Foucault's pendulum was a device for demonstrating the Earth revolves around its axis. It was first set up in the Pantheon Dome in Paris in 1851. The pendulum, made of wire with a round weight that weighed 61 pounds and was 220 feet long. The pendulum was set into motion and would swing back and forth following a line on the floor. After a while, it deviated from that line in a clockwise direction. It took 31 hours and 50 minutes to make a full circle. That's approximately 11 degrees per hour. The same demonstration, if conducted in the southern hemisphere, would rotate in a counter-clockwise direction, much the same as water going down a plug hole. It is important to realise the pendulum, although appearing to rotate, was in fact still on the same plane as when it was first started. It was the Earth that had moved. The picture you see here is a small model I've made to demonstrate these principles. Although my pendulum is extremely small, the weight you see here, which is in a rest position, is about 6 pounds in weight, and it hangs on fishing line which is no more than about 9 feet long. But it will serve to demonstrate the principles involved. In order to put the pendulum into motion, it's usually held to one side and left for an hour to settle down, whereupon it's released. Most demonstrations throughout museums in the world, including the Science Museum in London, use some form of silken thread to hold the weight to one side. When it's completely settled down and there's no wobble or anything else, the threads are set fire to. This releases the weight to swing without any bias that a mechanical release would undoubtedly produce. I decided on this model not to go down that route, but to use another type of release that I thought would have little, if any, effect, causing it to swing either to the left or to the right. And this I achieved by simply a battery, a bell push button or switch, and a length of fuse wire. Upon pushing the bell switch, the fuse wire evaporates and releasing the weight with no bias applied to its direction. This picture shows my release mechanism. It's very simple and comprises of a battery, a bell push, and a piece of fuse wire a couple of inches long, 5 amps, between the terminals. This model serves to demonstrate the principles. Here's my release mechanism, here's my weight and pendulum, and here's the track that it should follow. Let's release it. If this was the full-size model, it would swing for over a day. But because of the short pendulum, a few hours, and this will end up in the centre again, of course, due to its aerodynamic properties. This is a paw shape. Ideally, it should be a round ball. Round isn't particularly aerodynamic, but it is stable. I'll explain this later. If you was to stand where I am, this side, and look along the board, you'll see that already the pendulum has deviated away from the straight line. But as I indicated, the pendulum is still on the same plane it was when it was released, and will continue to be. We'll let it swing for a little bit. There might well be a very slight oval swing. I'm not going to go into the mathematics of why that is. You can look that up. But it's an interesting demonstration, nevertheless. So coming back to the mass of the weight, and the length of the pendulum, you want that weight concentrated at this end as much as possible. This might make very little difference to clock regulation, but in terms of what's being shown here, it does make a difference. And I'll try and demonstrate that, if I can, with an orange. We'll let this swing for a moment. Well, I'm sure by now you've probably seen enough of this, but this will go on for some time. Okay, let's deal with aerodynamics of the weight. Going to use this orange to demonstrate. It's as round as I could find one, and it matters not whether you vote from this way, this way, or that way, or any way. It represents a sphere. It has symmetry. So, in terms of a weight going through the air, it's stable, very stable. When the weight goes from right to left, on this side we have a pressure wave, because it's quite blunt. And on the opposite side we have turbulence and eddy currents. So this is draining the energy of a free swinging pendulum. And when it goes from left to right, that's our pressure wave and this is our eddies. But as I said earlier, it has symmetry. That makes it extremely stable. I'll see if I can demonstrate that. Here I have an airline and a steel ball bearing, and hopefully I can balance it on the end of an air stream. There we go. That's very stable. I can move it to the right, to the left, around, and it's quite happy to sit in the airstream to the symmetry. I'll be showing more on this later in the series. I hope you enjoyed that.